Hi everyone. In chapter 7, we're going to now begin our lesson on geometry, starting with section 7.1, which is about points, lines, planes, and angles. A lot of this will just be really important definitions, but there are certainly a few key relationships and quantities that we're going to want to know as we go through this section. I think most of us are familiar with a point. The notion of a point is it's a location in usually two-dimensional or three-dimensional space, and it's dimensionless. It has no thickness, length, or width associated to it. When we have 2 points in a plane, we can connect them via a straight line. The important thing as it pertains to the definition of a line is that a line extends infinitely far in two directions. So whenever we draw a line, we put arrows at the end to indicate that it doesn't stop. It extends infinitely far, in this case to the left, and infinitely far to the right. When we think about a plane is a two-dimensional shape and figure that extends infinitely far in two independent directions. Okay? For those of you that remember maybe like high school algebra, usually the one we kind of focus on a lot is the XY plane, where your two independent directions, for example, would be the ability to go either left or right, or up or down. So in a plane, we have two independent directions, and it extends infinitely far up, down, left, and right. We also have some other types of lines. So we've discussed that a line in general goes infinitely far to the left and to the right. If we have a line segment, that is a straight line that has a finite length. Here, this is the line segment AB. It starts at A and it ends at B. We can also have a half line, which is a line that has a segment endpoint and would extend infinitely far in just one direction. So this would be like a half line. And then we have a ray, which is very similar to a half line. The only difference here is that the point A is included in the ray, whereas in the half line, the point A would not be included. We also want to talk about an angle. Angles are a measure of rotation. If you have two identical copies of a line, or in this case of a ray, and let's suppose that they join at the point B, the amount of opening or separation between these two lines we would refer to as being angle B. We can also write it a few different ways. If it's not unambiguous, we can also refer to it as simply being angle 1, or you can label it according to points on the rays, where the middle point, which we call the vertex of the angle, would be in the middle. So this particular angle, we could refer to it as angle A, B, C, or you could refer to it as angle C, B, A. So oftentimes we have multiple ways to name an angle depending upon how it's configured and set up in a picture. We would say that BA and BC would be the sides of the angle, and the point B would be the vertex. It's where the two lines meet. For example, if we look at this configuration here, we would want to use one of our naming conventions above because there's three different lines that intersect at B. So if we tried to say angle B in this case, it's really ambiguous because there's three different angles one could talk about. There's this angle here, which I could label, for example, as angle A, B, C. We also have this angle here, which you could label as angle C, B, D. And we have yet a third larger angle, which would be this angle here, which would be angle A, B, D. Okay? And so, especially when you have multiple lines that join at a particular point, we need to be very clear as to which angle we're talking about, and that's why we have this naming notation. In example 1, we just kind of want to get some practice naming these angles. Here, we want to name the angle in part A in 4 different ways. One thing we can do is we could simply call it angle 3. We could also refer to it as angle S. according to the vertex because there's only one angle here. You could also call this angle RST, or we could refer to it as angle TSR. In part B, we want to write three different angles that have point B as their vertex. One such angle here would be angle ABC. We have yet another angle here. I could label this CBD, or you could even say DBC. That's the same angle. And then we have yet another one. I could label this angle ABD. So these would all be three angles that have B as the vertex. In our class, we're going to use degrees, which will be symbolized by the degree symbol as the measurement for the angles that we will use. 1 degree is defined to be 1/360th of a complete rotation. So if you were to rotate and do one complete revolution of a straight line and it would coincide with itself, one complete revolution is going to be 360 degrees by definition. And therefore, one angle, 1 degree, is going to be 1/360th of a complete revolution. Typically, if you were to measure these angles, you would use an instrument which is called a protractor. To measure angles, you would put the center of the protractor at the vertex. You would line the base of the protractor up with one of the rays, and then you could use the other ray, wherever it terminates, would be your measurement. So for example, if we look at this angle here, it's an acute angle, and this angle would have measure 40 degrees. So the measure of angle B would be equal to 40 degrees. The next thing we come to is some definitions of types of angles based upon the size of their measurement. An acute angle is any angle that measures between 0 and 90 degrees. A right angle is an angle that measures 90 degrees. Typically, whenever we have a 90-degree measurement for an angle, instead of doing the rounded angle measure like you'll typically see, usually we use like a hard kind of like bracket or like a corner piece to denote 90-degree measurements. We have the notion of an obtuse angle, which is any angle that measures between 90 and 180. And then a straight angle, which you can think of as half of a rotation. A straight angle would form a straight line, and those are going to have a measurement of 180 degrees. So a couple key definitions: acute, between 0 and 90. Right angles are 90 degrees. An obtuse angle measures between 90 and 180. And then a straight angle measures exactly 180 degrees. The next thing we're going to discuss is pairs of angles. Two angles that share a common side are referred to as adjacent angles. Okay. For example, if we look at angle 2 and angle 1 as they're measured here, these two would be adjacent angles. And the reason why they're adjacent angles is they share the common side BC. So segment BC both helps to form angle 2 and it helps to form angle 1, and therefore we would say that angle 1 and angle 2 are adjacent angles. If two angles sum to 90 degrees, they are referred to as complementary angles. For example, if I look at angle 1 and angle 2 in this picture, the two of them, when added together and taken in total, would give us this angle here, which we see, according to the picture, is going to be a 90-degree angle. So if two angles sum to 90 degrees, that pair of angles is called complementary. Okay. Examples of complementary angles would be things like 10 degrees and 80 degrees. Right? If you take 10 plus 80, that would give us 90. You could even have things like 40 degrees and 50 degrees, or something like 15 and 75, these would all be examples of complementary angles. We have a similar definition. If a pair of angles measures to 180 degrees, then they're referred to as supplementary angles. In this picture, we see that angle 1, the measure of angle 1, plus the measure of angle 2 would create the straight angle WXZ, which measures 180 degrees. So we would say that angle 1 and angle 2 are supplementary. One of the easiest ways I find to kind of keep these two definitions straight is if you compare the words complementary and supplementary alphabetically, the C comes before S. On a number line, 90 would come before 180. So the two that come first, complementary goes with 90, supplementary goes with 180. Let's take a look at the next question. They tell us that angle FEG would be this one right here, and angle GED are complementary. They tell us that GEF or FEG is 28. Find the measure of GED. So let's do our standard algebra trick. If we don't know what the measure of that angle is, let's call it x. We know that because the two are complementary, that means that they have to add to 90. So the measure of the one angle plus the measure of the other angle is going to be equal to 90 degrees. And then we can use our rules of algebra to solve for x. Simply subtract 28 degrees from both sides, and we would get x is equal to 62 degrees. So the complement of a 28-degree angle would be a 62-degree angle. Very similarly, in this example, we want to find the measure of SQP. They tell us that SQP, which is this angle here, is supplementary to angle RQS, which is 135. Let's denote the angle we're looking for. Let's call it X. If they're supplementary, that means that they add to 180. So X plus 135 equals 180. To solve for X, we would subtract 135 from both sides. And we would get that X is going to be equal to 45. So the measure of SQP is 45 degrees. Let's take a look at example 4. They say that two adjacent angles are supplementary and one angle is 3 times as much as the other. Find the measure of each angle. So we have two angles we're talking about. Just generically speaking, I'm going to call one angle A. I'm going to call the other one angle B. To set this question up, it's going to be one of our standard algebra type questions. Let's let X represent the first angle. They say that the other one is 3 times as large as the other. So if I call the first angle X, if the other one's 3 times as large, then it's going to be 3 times X, or 3X. So we come up with a variable expression first, and now we're going to use the relationship that the two angles are supplementary. That means that the measure of the first angle plus the measure of the second angle should add up to 180. We now have our equation. We can solve this for x. X plus 3x gives us 4x. 4x equals 180. We would divide both sides by 4, and we would get x equals to 4 goes into 80 45 times. As with all of our word problems, let's make sure that we're answering the question. The question said to find the measure of each angle. Well, we now know the measure of angle A. Our first angle is going to be 45 degrees, and the second one is supposed to be 3 times as much. So that one's going to be 135 degrees. The next types of pairs of angles we're going to look at is when you have a configuration of two intersecting lines. Let's call them L1 and L2. When two lines intersect, it forms four different angles that happen to be equal in pairs. Okay? Angles that are opposite or across from each other in this configuration are what we call vertical angles, and they're going to have the same measurement. So angle 1 and angle 3 are going to have the same measurement because they're vertical angles, as too would angles 2 and 4 are going to have equal measurement because they are also vertical angles. In the next example, they tell us that the measure of angle 1 is 40 degrees. And we're asked to find the measure of the other angles in this configuration. So we want to find the measure of angle 2, the measure of angle 3, and the measure of angle 4. The one that we can get immediately is angle 3. If we look at angle 1 and angle 3, those are vertical angles, so they're going to have the same measurement, which means that angle 3 is also going to be 40 degrees. In order to find either angle 2 or 4, notice that both of those are going to be supplementary with angle 1. If I take angle 1 and I add to it angle 2, that's going to give us a straight angle, which would be 180 degrees. So I can say this, that 40 plus, let me just call angle 2x for right now, 40 plus x is going to be equal to 180. You would subtract 40 from both sides, and we would get that x equals 140. So angle 2, as it turns out, is going to be 140 degrees. And then if we know angle 2 is 140, then that means that angle 4 also has to be 140 because 2 and 4 together are vertical angles, and they're going to have the same measurement. The next thing we're going to look at is when we have a pair of lines that are called parallel. Two lines are parallel, which we write with notation L1 is parallel to L2. It's that pair of vertical bars in between them. Simply means that those two lines do not intersect each other. So lines are parallel if they never intersect. And now we're going to look at a third line in this configuration, which is going to intersect both of those two lines. Okay. And we're going to call this line L3. That intersecting line is sometimes referred to as a transversal because it transverses or crosses both of our parallel lines. When two parallel lines are intersected by a transversal, it creates a total of 8 different angles. We can see up here where the L3 line intersects L1, we have a 4-angle configuration which is labeled 1 through 4. And then down here we have 4 more angles labeled 5 through 8 that are also present. Angles 3 through 6, 3, 4, 5, and 6 are referred to as interior angles. And the reason why they're called interior angles is because they're between the two parallel lines. Angles 1, 2, 7, and 8, which are outside of those parallel lines on the exterior, are referred to as exterior angles. If we look at the definition of alternate interior angles, so interior angles, alternate interior angles, are angles that are in the interior but are on opposite sides of the transversal. Okay? So for example, if I look at angle 3 here, which is an angle up top, the angle on the opposite side of the transversal on the bottom picture would be 6. They're interior angles. They're on the opposite side of the transversal, one with line L1, one with line L2. These are alternate interior angles. The other pair of alternate interior angles would be angle 4 and angle 5. And the important thing as it pertains to this is that alternate interior angles have equal measures. So whatever the measure of angle 3 is, that's also going to be the measure of angle 6. And similarly, whatever angle 4 measures will also be the measure of angle 5. So these two and these two will have the same measurement. We have a similar notion for alternate exterior angles. Alternate exterior angles will also be equal in measure. So if I look at the exterior angle up top, which is 1, the angle on the other exterior on the opposite side of the transversal would be 8. 1 and 8 are alternate exterior angles, and they're going to have the same measurement. And the other pair of alternate exterior angles would be angle 2 and angle 7. Those two are alternate exterior, and therefore they're going to have exactly the same measurement as well. We also have the notion of what's called corresponding angles. Corresponding angles is a matter of finding one angle in this upper position, this upper location, that plays the same role as the angle in this bottom configuration. What I mean by that is they would lie in relation to the parallel line in the same direction, either above or below, and on the same side of the transversal, either to the left or to the right. So for example, angles 1 and angles 5 are going to be corresponding angles. The reason why they're corresponding is they both lie, first of all, above their respective parallel line, as well as to the left of the transversal. And corresponding angles will also have equal measurements. So 1 and 5 are corresponding. The next pair of corresponding angles would be 2 and 6. They both lie above their respective parallel line, and both of them are on the right side of that transversal, meaning the right side of L3. So 2 and 6 are corresponding, which means they're going to have the same measurement. The next one we're going to look at is going to be angle 3 and angle 7. Those are both corresponding angles. They both happen to lie below their respective parallel and to the left of the transversal, so they're going to be equal in measurement. And then the last pair of corresponding angles would be 4 and 8. They're both below the parallel and to the right of the transversal, so they too would have equal measures. With all of this information, it makes it very easy to determine the measures of all 8 of these angles if you simply know the measure of 1. So let's suppose in example 6 that they tell us that angle 2 measures 50 degrees. And from that, we want to find the measures of the rest of these. And I'm just going to write them very briefly. Instead of saying the measure of, I'm just going to write down the angles. Let's go off of the easiest ones first. So first of all, if I know angle 2 is 50, then automatically I'd also know that angle 3 is 50 as well, because 2 and 3 are what we call vertical angles. If you just look at the intersection of L1 with L3, 2 and 3 are vertical angles, so they have to have the same measurement. So that tells us that angle 3 is also going to be 50. From there, I can also get the measurements of angles 6 and 7. They have to be 50 as well. Angle 2 and angle 6 are going to be what we call corresponding angles. The role of angle 2 in this top configuration is to the above and to the right of the transversal. That's the same thing as angle 6. So 2 and 6 are equal via corresponding angles. So this is 50. And then once I know that 6 is 50, then 7 is also going to be 50 because 6 and 7 are vertical angles. Equivalently, you know that 2 and 7 also have to be equal because 2 and 7 are going to be alternate exterior angles. Similarly, once you knew that 3 was 50, we also would have known that 6 was 50 as well because 3 and 6 together would be alternate interior. Okay. So that gives us 3 of them right off the bat. The fact that angle 2 measures 50, we can use that to find angle 1, because 2 and 1 together have to be supplementary. Let's call angle 1 x. X plus 50 has to add up to 180. Subtract 50 from both sides, and we would find that the measure of angle 1 is going to be 130. Now that we know that angle 1 is 130, angle 4 also has to be 130 because 1 and 4 are vertical angles. 1 and 5 are going to be the same, so 5 is also 130 because 1 and 5 are corresponding angles. And then 8 also has to be 130 because 5 and 8 are vertical angles, and so those have to be equal as well. So working it out, we found the measures of all of the other ones simply by knowing the relationships of our pairs of sides.